Hello everyone. In the previous lecture, we were discussing a rather mathematical looking theorem called the generalization of Castigliano's theorem of least work, but that had mostly to do with the modified form of the or a modified definition of the complementary energy. And we had said that that proof would pave the way for something rather useful. Uh, in fact, the most useful thing from this chapter on energy methods called the Castigliano's theorem. Okay, so we are going to discuss that in this lecture. In fact, all of our discussions starting from the first lecture of energy methods, we have been building up towards this particular theorem. Okay, so this is the famous Castigliano's theorem of deflections. Castigliano's theorem on deflections. All right. So again, instead of writing out a grand formal statement of this Castigliano's theorem, which of course is very much present in our lecture notes, let me just try to describe what this theorem is telling us, and then we'll discuss something about the proof. Okay. So as usual, we consider this general three-dimensional body. Okay, maybe use a different color again. This general three-dimensional body. And just as in the previous discussion, we considered a part of the surface over which the tractions were specified. So also we'll discuss here. So over this entire surface, but we'll of course change this a little bit here. Okay, so over this entire surface, the tractions are specified. Okay, tractions are specified over here, and over the rest of it, let's say with this blue color, we specify that over the rest of it, which is S2, it is the displacements which is specified. Okay, now the only difference from that previous consideration here is that over this part of S1 there will be certain spots. Okay, let's just call spots for now. Over the spots together, so let's say let me use a different color here, maybe this one, green. So over this little spot here, maybe not such a wise choice of color here, but anyway, over this spot here and over this spot here, over this spot here, some point forces are acting. Okay, so something like this. Okay. Now, ideally, you would think that these point forces should be acting on points, but as we'll discuss as part of the proof, is that these point forces are really a manifestation of a very concentrated distribution of forces. So in that sense, these are acting on certain spots, and the entire area, so to speak, that is covered by these spots, that will say all these green colored things together. Let me not point arrows, be only confusing. So over these green things, they together will constitute S naught. Okay, so so this S naught, it only pertains to these green spots. Okay, I don't know how well this video will get rendered, but anyway, so these are the green spots over which the point forces are acting. These are together S naught. All right, so so you understand that when I write this S1, it basically excludes all these spots. Okay, so this is S1, the part of S which does not include S0, which does not include S2, that is S1. Okay, so with this much of an understanding, what this theorem, Castigliano's theorem of deflections, is telling us is that if you wish to find out, before I state that, one very important point is that over this S2, I have said that the displacements is specified, but as a very special case, you note that such displacements are specified as a special case to be 0. Okay, this is very, very important. So as an example of this, maybe you can consider something like like a cantilever beam. Okay, okay, cantilever beam under tip load. So here, over this part of the cantilever at this end, the displacements are specified, but they are specified to be zero. Okay, here is the point force, and over the rest of it you have zero traction. Over the rest of the body you have zero traction. So that zero traction is also something specified, let's say. Okay, so in that sense, and you can have other such more plain examples from our engineering perspective. Okay, uh, for now I'll delete this, and we'll go on to such considerations of beams when we apply this Castigliano theorem of on deflections later on. But for now we just want to discuss some of the details of it. So what the Castigliano theorem on deflections is telling us is that the deflection that will occur at the points of applications of these forces, of these various forces, in the direction of the applied force. Okay, this is very, very important. So what we wish to say is that the deflection of a particular force, okay, in the direction of that force, that will be given by the partial derivative of the complementary energy with respect to F, where F is any one of these point forces. Now, before launching into any detailed discussion, it is extremely important to note that you should think about the you should think about uh, these point forces in a slightly different fashion from the way that these tractions and displacements are specified. What I mean to say is that uh, when I say that I have specified this traction vector, the first variation of that is going to be 0. But you note that if you were to consider the forces, these point forces, these green colored point forces, to be similarly specified, then considering a partial derivative with that as the magnitude of that as the independent variable, that would certainly not make any sense. So what we are saying here is that you consider these point forces to be variable, and we wish to find out what will be the values of the displacements in response to those variable forces. Of course, it does not mean that you will not be able to solve concrete problems, and you will see that we will be very much able to do that. But in the application of Castigliano's theorem on deflections, it will be important to take them in a very general variable kind of fashion, and then at the end to, to specialize them to their specific values. So all these things will be clear as you go into the more details of the Castigliano's theorem, and finally everything should be crystal clear when we come to the actual application of this Castigliano's theorem on deflections to problems. Now, for some of the details of this theorem regarding its proof. So, fair warning, first of all, as you may have noticed, there will be a few things to be extremely careful about, and all throughout the proof, you may feel a little bit dissatisfied uh, with certain critical junctures, but as I said, fair warning, so brace yourself. And even before we start the proof, we have to go into a little pre-theorem kind of thing, which is referred to as the theorem of the mean for integrals. Okay, so it sounds like the mean value theorem which you studied in your I think in your high school maths, in your plus 2 maths, but uh, but it's not exactly that. Okay, it's something different. The theorem for the mean for integrals, this is something which we will require very much as part of our proof of this Castigliano's theorem on deflections. So instead of digressing in midway through the proof, let me just state it beforehand, and later on I'll just use it. And please note that I'll state this theorem without any proof. Okay, we could have gone into into the details of it, but that's just a distraction for our current purposes, so I'll resist the temptation. So first of all, a pre-theorem kind of thing. Okay, so pardon this kind of a nomenclature, but it's just to keep things uh, nice and simple. Okay, so what we say is that suppose you have two functions, uh, two nice real continuous functions. I should say that f of xy and g of xy, okay, defined over some area A, and you have this kind of of an integration over the area A, where you have f of x, f of xy multiplied with g of xy over the entire area. So what this theorem, theorem of the mean for integrals, in fact I can write that. Okay, so this is theorem, theorem of the mean for integrals. Okay, so this thing is going to be equal to a times g of xy dA, provided, so even before that let me just say what k is, uh, where k is some value of this function f of xy within the area A. It is some value. Okay, so f of xy may take various values within A. So what this thing is telling us is that it will be equal to k times this, where k is some value of f of xy within A, and this thing can be written provided g of xy, and this is the crucial thing to note, that g of xy, it does not change sign in A. So always you will not be able, just because you have two functions over an area, it does not mean that you will be able to write it like this. Of course not. So provided g of xy does not change sign within A. Okay, so it cannot be that one, at some places within A g of xy is positive and in other places within A g of xy is negative. No, if it is positive somewhere, it should be positive everywhere within A. If it is negative somewhere, it should be negative all throughout A. Only then this theorem will hold. Okay, so this is the theorem of the mean for integrals, and we are going to use this in our proof of Castigliano's theorem on deflections. Okay, uh, so we launch into the proof now, and please note the pitfalls and the special things that I had mentioned earlier. Okay, so we are going to consider this f as something variable, and which we'll actually use. We'll also use the understanding that this f is actually generated also through some kind of fractions, but which are distributed over very small spots, uh, and so let's proceed. And uh, even though we had mentioned earlier that the what we had discussed in the previous lecture, that the modified complementary energy, uh, that the theorem associated with it, so which will help, it will help us in this theorem, Castigliano's theorem on deflections. But it is not that we are absolutely going to start from the expression, the first variation of capital psi is equal to 0. We're not going to start from that. Rather, the proof of that earlier theorem is going to help us. So so there are there's some careful business involved. So let's give it a try. Okay, what we'll start with is, if we just look back a little bit, uh, you see, uh, somewhere around here, okay, we had started with this delta u dash, and we had ultimately arrived, uh, not ultimately, intermediately we had arrived at this expression, integration of ui delta ti ds, okay, over the entire surface. So our point of attack for the proof of the Castigliano's theorem on deflections will be from this part and not from the ultimate statement which we had proved here. Okay, we are not going to start from here, rather we are going to start from that intermediate step. Okay, so we have this delta u dash is equal to integration over the entire surface ui delta ti ds. And as before, we subdivide this integration over uh, over the S naught on which the point forces, so to speak, are acting. But please note that the meaning of writing this Ti is that those point forces are actually generated through a concentrated distribution of some traction. Okay, you really don't have physically a such a mathematically defined point force. Okay, uh, next over S1 we have this ui delta ti ds, and over S2 again we have ui delta ti ds. Now we take these things. So you see over S1 we do indeed have the traction specified, and at the very beginning of our discussion uh, I had carefully noted that we should be making a distinction between the way that the tractions are specified over S1 and the tractions are specified over S0. Okay, so there is no question of variability in the tractions because they are indeed specified in a constant fashion over S1. So here this thing is going to be 0 because Ti is actually specified there over S1. This is extremely important to note. Next, for this integration over S2, it is the Ui which is specified. Okay, you can go back to our initial statement here where you note that this u vector is equal to 0. It is the displacement is specified, but the value is specified as 0. So here it is this thing which is actually 0. All right. So what we are really left with is just this integration over the S naught. So S naught, mind you, is those little green spots over which the point forces are being applied. And again, I'm telling you that these point forces are generated through some concentrated distribution of these fractions. Now, uh, what we would like to do right away is to apply our pre-theorem. That theorem we had discussed in the previous slide, the theorem on of the mean for integrals, that we are going to utilize right away on this integration. You see that one was defined over a certain area. This is also defined over a certain area S naught. So, and there also we had two functions f of x, xy and g of xy. Here also we have two functions, ui and this delta ti. This is involving a first variation, but no matter. So what we the starting point of our logic or our argument of utilizing that theorem of the mean for integrals is this, that over these little spots we do not expect the tractions to change in sign. Okay, so uh, so over the little region S naught, we do not expect Ti to change sign. In fact, you can write this as delta Ti. Okay, so in that sense, this delta Ti is like the counterpart of the g of xy in that theorem, which means that we can write this delta u dash as ui. We take this outside, but note that the value that we specify for this thing is not actually the ui that we are taking out, rather a certain value of this ui within the region S naught. So just like in the statement of the theorem of the mean for integrals, we had taken out a certain value k of f of xy, where k was any a certain value within that region. Similarly, this ui bar is a certain value of the ui function within the region S naught. Okay, so we write this clearly as where ui bar are the components of the displacement vector ui at some point within S naught. At which point we don't bother, but at some point, sorry about that, at some point within S naught. Okay, now we are left with this integration over this delta ti. All right, so let me go to the next page here and note that for this so-called point force, okay, so for this for a point force uh, Fi, okay, will have Fi, as we have been saying all along, this Fi is actually generated due to this distribution of traction vectors. Okay, so you can think of it like this. If you're uncomfortable with the fact that I have written this S naught to depict uh, the collection of spots, and here I am writing for each force this S naught, so you can maybe say this is S naught 1, and then maybe for another force that could be S naught 2 and all those things, but I'm not over complicating the notation. You understand, you're all engineers, so I'm sure that you're practical minded enough to understand what's going on here. Okay, so for example, if you just take 1 point force, it will resolve all your doubts here. uh, and we can easily extend that by some change of notation to more point forces. Okay, but that's not the point here. The point here is that we would like to uh, arrive at an expression that we were developing earlier in terms of this Fi. Okay, so towards that end, we write like this, and then of course we can write this as we have done earlier. We take the first variation within the integration sign. Okay, which means that whatever we had earlier obtained, this delta u dash, that can be written as ui bar. Please do not forget this bar. This is very, very important. This is not ui. This is a specific value of ui within some point within that S naught, that little area S naught. So this entire thing can be written as delta f. Okay. So now we are getting closer and closer to our ultimate statement of the Castigliano's theorem on deflections. What we'll do is, we note that this delta Fi is very much a force vector. And being a vector, we can write this Fi as the magnitude of F. Okay, please note that it is this magnitude which will ultimately come into picture in our ultimate statement of the Castigliano's theorem on deflections. You note that del F was there, okay, in that original statement, that F is this F, the magnitude of the force. Okay, so that multiplied by the unit vector along F. Okay, so this is just like saying that if you have any vector v, okay, so that is the magnitude of that v vector, times the unit normal, is the unit normal or the unit vector along the force along that vector. So in same fashion we write like this. Okay, uh, so we know this, and so what we can say is that delta u dash is ui bar ni delta f. Please note that this ui and this ni, this together is like a dot product. Okay, now what will that what will be the result of that product? What will be the meaning of that? The meaning of that, okay, so if we actually write, so this is a vector, this is a vector, we have a dot product, the result will be some scalar. So that scalar, the meaning of that scalar is basically that uh, you see this is some displacement vector at a particular point within S naught, and if we take the so the meaning of this scalar result will be just the component of this vector, of this displacement vector along that n direction. I repeat, if I write the result like this, it basically means that we have taken the component of this ui bar vector along the direction of this unit vector. But what is the direction of this unit vector? It is nothing but the direction of this point force itself, because that is what it is depicting, which means ultimately what we have written here is that we have written the component of the displacement vector at a certain point within S naught in the direction of the applied force that is acting over that spot. Okay, so you pause for a moment here and think about what I just said. This is the crucial statement. The rest of it is just mathematical jugglery to arrive at the final statement, but this is the heart and soul of this theorem. Okay, so delta u dash, we have managed to write it as a product of two things. First is this displacement vector uh, at a point within the S naught, but taken in the direction, its component taken in a direction along the applied point force multiplied by this first variation of the magnitude of that point force. Now uh, we are almost at the end, but before that we have to take a little leap of faith in writing something for this delta u dash. So you understand that all throughout our discussions of this chapter, whether we are talking about internal energy, strain energy, specifically strain energy, complementary energy, we had in our brain that somehow these had connections with the strains and stresses. Now what I want you to think is that uh, this strain here, whatever it may be within the body, uh, manifested in terms of the deformations and everything, that is ultimately occurring as a result of the application of this force. And also you note that we are considering very much the variability of this force. So is it not possible to write the connection directly between this complementary energy with the variation of that force? Okay, so earlier we had written things like del u dash, del epsilon pq and sort of things, uh, those kinds of things. What I want you to now think is that directly we want to make a connection between this u dash and the force which is variable, because the strains that are being generated in the body, the strains represent the deformations. Those deformations are actually brought about in response to these forces. So what we write here is that this is del u dash del f delta f. Okay, and again mind you that suppose there were some dependence on temperature or things like that, we would have to add terms here to write things like plus del u dash del t, delta t, and so on and so forth. Suppose if there was some dependence on the electric field and things like that, would have to keep on adding terms, but we don't have those complications here. So we just stop here to write it like this. Now if you compare this one and this one, okay, so uh, maybe I call this as hash 3 here and hash 4. So comparing, maybe I write this in the next. So comparing hash 3 and hash 4, we have delta u, sorry, we have uf bar, the component of the displacement along the direction f, to be equal to del u dash del f. And this is nothing but our original statement for the Castigliano's theorem of deflections. So it is hence proved here. Okay, so the path to this had been, it has been beset with very careful remarks and statements. But I hope this will give you some sort of satisfaction at the end that we have managed to arrive at this thing. And it is in this form that we are directly going to apply it to problems. Now, one very important note is that if our material behavior is such that it is linear elastic, then there is no difference between the complementary energy and the strain energy. Okay, so for linear elastic materials, that is for Hookean kind of materials, for linear elastic materials, uh, okay, so u dash is equivalent to u, and for those things we can directly write uf bar is equal to del u del f. Okay, and it is this particular form which is mostly used uh, in many undergraduate textbooks if they do deal with energy methods. So most many undergraduate textbooks, they don't deal with energy methods, but there's some good textbooks which do use, and when they do, mostly it is in this fashion that they write the displacement in terms of the directly in terms of the derivative of the strain energy and not in terms of the complementary energy. But you see that for uh, I should make a remark here that this is certainly not true for nonlinear materials or for nonlinear material behavior. Okay, this is very, very important to note, and we will see an example of this. Okay, uh, so with that, as far as the theory part of this energy methods is concerned, we are done. So we'll discuss problems. You'll also do some problems. All right, with that, I end this lecture. Thank you very much.